Hi everyone, today a video in the electrochemistry series looking at the different types of batteries. So there are several different types of batteries, but batteries are all based on the principles of electrochemical cells. These are all the principles that we've looked at in the past two videos of this series. And strictly, a battery refers to a number of cells connected together. But in everyday speech, we tend to use the word to mean any portable source of stored electricity. Now, batteries can be non-rechargeable, they can be rechargeable, they can be portable, and there's a relatively new type called a fuel cell. Now, we're going to go through all of these examples, but the two really important ones, if you're studying the AQA exam board and to know the equations for, are for the portable and the fuel cells. So the first type to look at here is a non-rechargeable cell. This does exactly what it says on the tin. It's a cell which we cannot recharge. So once we've used up the electricity that we can generate from it, we can't get any more out of it and we can't recharge it back up. Now, one of the examples of this is something called the Daniell cell. It's made from zinc and copper electrodes. So remember that our electrode is the same thing as a half cell. So our zinc electrode, our zinc half cell, is a solid zinc rod dipped into a solution of its own ions. And we also have the same thing for the copper. We have a high resistance voltmeter to measure the potential of this cell, but normally it would just be a wire connecting the two. And we also have our salt bridge to neutralize any sort of build-up of excess charge that occurs. And so this cell operates on the principles that we've been looking at in the previous videos, that electrons flow from negative to positive. They flow from a more reactive metal to a less reactive metal. And if you double check the electrochemical series, you'll see that the zinc half cell has a more negative potential than the copper half cell. And so therefore our electrons flow from the zinc, which is our anode, to the copper, which is our cathode. Now, while this cell works perfectly fine, it generates electricity, it wasn't practical for portable devices because of the liquid that it contains. Because we now have solutions of zinc ions, solutions of copper ions, it just wasn't practical because it contained these solutions. Think about your mobile phone, think about your laptop, various portable devices. It wouldn't be particularly practical to have lots of solutions and lots of liquids in them. Now, another type of cell is based off zinc and carbon. It's called the Lachance cell. And here the carbon acts as an inert electrode. It's similar to when we've seen platinum being used, for example, if we had gases or if we had solutions that just contain ions and no physical metal, no physical solid metal. We could use platinum as our inert electrode. Here we're using carbon as our inert electrode. And this type of cell here is the basis of most disposable batteries. And the electrolyte, the key thing here, the electrolyte is a paste rather than a liquid. So it's better in terms of being a portable device. We don't have to worry about carrying around actual solutions, actual liquid with us. It has a paste inside. And so the two equations that we have here, you don't need to remember these equations if you're on the AQA exam board, but our zinc is oxidized. So our zinc is the anode. Remember our mnemonic of red cat and ox. Our zinc is oxidized, and therefore it is the anode, it's the negative electrode. This is the more reactive electrode. And then we have the ammonium ion being reduced to ammonia and hydrogen. And so if we combine these two redox equations together, we get our overall reaction as being the ammonium ions plus zinc to produce ammonia, hydrogen, and zinc 2+. And it gives it a cell potential of 1.5 volts with the zinc as the negative terminal. Now, the hydrogen gas that we end up producing, the H2, is oxidized to water by a manganese dioxide species that we have in there as well, MnO2. So the hydrogen gas gets oxidized to water, and what this does is it prevents a buildup of pressure. Obviously, if we keep producing hydrogen gas and we don't have any release for it, this is going to build up pressure and that's unsafe. So a way to get around that is to have this manganese dioxide in there, MnO2. This oxidizes the gas to water, and it also helps with our ammonia because our ammonia that we produce, again, a gas, we don't want to build up a pressure. If we have water, our ammonia can dissolve in the water of the paste. Now, as the cell discharges, the zinc is used up, and the walls of this battery, essentially the zinc anode, the walls of the zinc canister, become thinner and thinner, and they're prone to leakage. And so the ammonium chloride electrolyte, that's where we get our ammonium ion from, an ammonium chloride paste. This is acidic and it can be corrosive. So you have to be careful with one of the reasons that we don't recharge these cells is because the more and more times we do we allow this reaction to occur and to generate electricity, those walls become thinner and more prone to leakages. And so there are many, many variants of this type of cell, and the particular one that we'll use, i.e. the particular half cells that we actually have in our cell, all depend on the application in terms of what the voltage requirement is, what the potential requirement is, what current we need, what the size of the battery is, what the cost requirements are. Now we use powdered zinc. This has a higher surface area, it allows for higher currents. And we can also sometimes, instead of casing it in the zinc, we can actually case it in a sort of outer steel container. And this would prevent a leak. But obviously if we're putting more materials in, that also increases the cost and the weight of our cell. So it's all factors to consider. Now we can start to look at rechargeable batteries. So we looked in a previous video how about we could work out the feasible direction for an electrochemical reaction. And the feasible reaction is where we have our electrons flowing from negative to positive, the more reactive metal to the less reactive metal. But rechargeable batteries can be recharged by reversing the cell reactions. So now we're moving in the non-feasible direction. Essentially, we're forcing the electrons to go from positive to negative, which we know they don't do on their own. So this has to be done by applying an external voltage. And the external voltage is greater than the voltage of the cell, and this drives the electrons in the opposite direction. You can think of it being akin to an endothermic reaction, where we have to actually supply energy in order for these reactions to happen quite often. And so an example of this is a lead acid battery, and this consists of two lead coated plates. You can see we have just sort of elemental lead and also lead oxide, and these are dipped into sulfuric acid. And so we'll have our when we discharge, the battery will drive the electrons from the lead plate to the lead oxide coated plate. And so we can see here that we have our sort of positive and negative terminals. And I've drawn this cell actually the other way around, so the negative is on the right rather than on the left. But you can see that our lead cell, our lead half cell there, our lead electrode is the negative, the more reactive metal, and our lead oxide is the more positive metal. You can also notice I've used the symbol I. I denotes current. We talked in the last video about the difference between electron flow and conventional current. The electron flow goes from negative to positive. Conventional current is the opposite, going from positive to negative. But in this case, our electrons would flow from the lead to the lead oxide, and this would be our feasible reaction. And so we can write these equations here. So essentially we have our lead combining with sulfate anions to produce lead sulfate and 2 electrons. So our lead has been oxidized. That's what we expect. It's the more reactive metal. It would have the more negative half cell value. And then at the other electrode, our lead oxide reacts with H+ ions, sulfate anions, and 2 electrons to produce lead sulfate and water. And so our lead oxide has been reduced. So in this case, we have our, remember, red cat and ox. So our lead oxide is being reduced, therefore it's the cathode, positive electrode. Our lead is being oxidized, and therefore it is the anode. And so we can write our overall equation simply by combining those two half equations. But the key thing is that being rechargeable, what we've written there is the feasible direction. When we recharge it, we force our electrons to go from positive to negative. So now we get the opposite reaction occurring. We go in the opposite direction. So the next type to look at is a portable battery. And so the rechargeable lithium-ion cell is widely used. So this is kind of the battery that we'd see in mobile phones, in laptops, lots of portable applications. Now it's very, very light because lithium is the least dense metal. That's important. You don't want your battery to be really, really heavy. If it's a portable application, we need to carry it around with us. It also needs to be able to be recharged. Wouldn't be very useful if once we'd used the electricity from that cell, that was it, the battery was dead. So it's important that we can recharge it, that we can go in this non-reversible, non-feasible direction. And actually, in this case, the electrolyte is a solid polymer, and so any kind of risk of leaking is reduced as well. Now, the positive electrode is a lithium cobalt oxide, and the negative electrode is carbon. Now, these are arranged in layers with the solid electrolyte in between. And so the equations that we need to know for this are first, and I've taken both of these directly from the electrochemical series, that we have our lithium ion reacting with an electron to produce lithium, and we have a lithium ion reacting with neutral cobalt oxide plus an electron to make this lithium cobalt oxide salt essentially. Now, if you actually look at the potentials of these, we see that the lithium ion with plus an electron to produce lithium, that's our more negative potential half cell. And so this is the one that will be oxidized, will lose the electrons, it's the better reducing agent. And so that will be our anode. Remember, red cat anox, so it's the negative electrode, this is our anode. And therefore our other equation with the cobalt oxide in, that must get reduced. And so therefore it is our cathode, the positive electrode. So we need to reverse the direction of our lithium half equation. So we have lithium going to lithium plus an electron. And then we have our other half equation in exactly the same as we had it before. So lithium plus cobalt oxide plus an electron to produce the lithium cobalt oxide salt, the ionic compound. Now when we combine these two half equations together, our electrons are already balanced, so we just write all the reactants on the reactant side, all the products on the product side. We end up with this full equation here. So lithium plus the lithium cation plus cobalt oxide plus an electron goes to the lithium ion plus an electron, and then plus this lithium cobalt oxide ionic compound. And so once we cancel out the electron on both sides, and we can also cancel out the lithium cations on both sides, we're simply left with lithium plus cobalt oxide to produce the lithium cobalt oxide ionic compound, the salt. Now, the carbon electrode that we use is powdered graphite. This acts as a support medium. And the really key thing, again, the idea of powdered, it allows for higher currents, as we saw before, but it also allows the reaction to occur in the absence of water. And this is really, really important because lithium reacts very violently with water. You might have seen videos of lithium metal being put into water and you get the fizzing, you get sometimes small flames appearing. That's because we have our lithium reacting with water to produce lithium hydroxide and hydrogen. So it's really important that we exclude water from these cells. One for the safety aspect of, so it doesn't react with the lithium. The other being that obviously we talked earlier that portable batteries aren't particularly practical if they contain liquids. So the last type of cell to look at is the alkaline fuel cell, or the alkaline hydrogen-oxygen fuel cell. Now this looks to be an extremely green type of battery, type of cell, because essentially the overall reaction here is that oxygen reacts with hydrogen to produce water. So our only byproduct of this is water. That's not a harmful substance. In fact, it's good to be able to produce water. And so our alkaline hydrogen-oxygen fuel cell has two electrodes of a porous platinum-based material. We need the platinum, essentially the platinum for the platinum electrodes here because we have hydrogen gas, we have oxygen gas. Both of these are solid conducting metals, so we need to have an inert conductive metal in there for the electrode. That's our platinum. These will be separated by a semi-permeable membrane, and the electrolyte is a sodium hydroxide solution. And so hydrogen enters at the negative electrode. We know our negative electrode is our anode, and our anode is where oxidation happens from red cat anox. And so our hydrogen is oxidized, it releases electrons. These electrons flow through the circuit to the positive electrode, and that's where our oxygen enters. So that must be our cathode, and we know that where the cathode is, that's where reduction happens. So the oxygen is reduced. And so the positive electrode accepts the electrons, and the hydroxide ions that are produced from this travel through the membrane. This is why we have to have this semi-permeable membrane. They travel through the membrane towards the negative electrode. Now the overall effect of this is that hydrogen and oxygen react together to form water. It's exactly the same reaction we can think of as if we burnt hydrogen and oxygen. But the key thing is that we don't have to raise the temperature to do this. We can do this at room temperature. And so there's, importantly, no production of nitrogen oxides, which can occur when hydrogen is burnt directly. So if we look at our equations for this, we have two lots of water reacting with two electrons to produce hydrogen and two hydroxide anions. That gives an E cell value of negative 0.83 volts. And we also have oxygen reacting with two lots of water and 4 electrons to produce 4 hydroxide anions. And this is an E cell value of plus 0.4 volts. Notice that those essentially are taken from the electrochemical series. They're written as reductions. And so we can look at our E cell values to see which one is the more negative. We're using the same principles that we've used in the past couple of videos to be able to work out what the feasible direction of our cell is. And so we can see that our hydrogen equation, the top equation, has the more negative potential. Therefore, it is the better reducing agent. It is the one that is going to be oxidized more easily, and it's the one that's going to lose the electrons. It's also going to be the anode because of red cat anox. It's oxidized, and therefore it must be the anode, the negative electrode. Our other one, our oxygen equation, therefore must be the cathode, and it must be where the reduction takes place. And that's true because we have our more positive potential value. So the first thing we need to do is to combine these two half equations. We need to reverse the direction of our hydrogen equation because at the moment it's written as a reduction. So we need to reverse it to write it as an oxidation. And to cancel out our electrons, we also have to times that equation by 2 so that we have 4 electrons on either side. And so that's the red equation you see there. We've multiplied it by 2 and reversed the direction of it. And then we combine our two half equations, write all the reactants on the reactant side, all the products on the product side, cancel out anything that appears on both sides. And so overall we end up with oxygen plus 2 lots of hydrogen producing 2 lots of water. And we can calculate an E cell value for this. Remember that when we write our cells down in this orientation with the anode on the left and the cathode on the right, that our E cell is the right minus left. And so when we put these numbers in, we find we have an E cell value, the feasible direction giving an E cell value of plus 1.23 volts. So at first sight, this fuel cell looks incredibly green, as we said on the previous slide. The only product is water. And so this is unlike many other sources of electricity where we end up also producing carbon dioxide. So at first sight, you might think, well, why isn't everything now made of fuel cells? The problem is that most hydrogen is made from crude oil. That's a non-renewable resource. We could also get hydrogen from the electrolysis of water, but again, that requires electricity, and typically the main source of electricity is through burning fossil fuels, producing carbon dioxide. And one of the big problems really is that if we were to, for example, power all of our vehicles by hydrogen, this would need a hydrogen infrastructure. So we'd have to get rid of all the petrol pumps, all the diesel pumps, and have a whole new hydrogen infrastructure. Now you can imagine the difficulty in having the whole, not only just maybe the whole country, but the whole world having a hydrogen infrastructure. It would take an awful lot of planning, an awful lot of money to be able to build all of that. And another key problem is that it's quite dangerous because hydrogen is explosive and it's highly flammable. One of the most well-known examples of this was the Hindenburg airship. That was filled with hydrogen and that very spectacularly caught fire and killed all the people on board. It's also very difficult to store and transport because hydrogen is a gas. So again, you have the safety concerns of transporting a large sort of a tanker full of explosive and highly flammable gas. And so it's very difficult to store and very difficult to transport as well. So even though it looks very green, actually there are quite a few problems with a hydrogen economy. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on our tuition website. I offer online tuition for chemistry, so please check my tuition pages if you're interested in that. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.